All right, welcome to Lab 10, last lab of the semester. Congratulations for making it this far, and good luck with the rest of the semester in your exams. This week, we're going to talk about algorithm families and EP. A few announcements. As always, quizzes handwritten are due this Friday, next Friday. There's a survey that's due the 6th, which is I think Friday, might be Tuesday or something. Make sure to do that. There's a link right there. Project 4 is due the 9th. You got a week on that. And another thing to note is when you're doing the autograder for Lab 10, it's pretty difficult. We give you a hint, a really substantial hint that you can use, and it pretty much gives you the recurrence relation and solves the problem for you. However, I highly recommend that you try to do it without the hint. It's a difficult GP problem, and I would say that it's probably a difficult, similar level of difficulty as one you could see on the exam. So if you're able to figure it out on yourself, by yourself, it'll be great practice for the exam. And then, the thing we've all been waiting for, we got the final exam coming up. Wednesday, the 15th, 8 to 10 a.m. If you need any alternative exam requests, make sure to send an email to admin. Any questions on announcements? Let's change our color. All right. Okay, today we're going to discuss algorithm families, Dijkstra's algorithm, permutations, and then DP. So here are all the algorithm families. To start, we have brute force, which is just guarantees the optimal solution, but it's slow. Brute force solution to searching for a number in a sorted array might just be doing a linear search, right? When you could do a binary search. A greedy algorithm would be one where you're picking the best solution for the information that you currently know. So you're making the best decisions along the way, depending on the information you currently know, and that happens to give you the optimal solution in the end. Greedy algorithms that we discussed were ones for the MSTs like prims and Kruskal's. You have divide and conquer, which are combining solutions to subproblems like merge sort. And we have backtracking. Backtracking uses recursion, and they're for constraint satisfaction problems. And constraint satisfaction problems are one where you want to find if there is a solution. It might not necessarily need to be the optimal solution, but just whether or not one exists. Whereas branch and bound is a similar algorithm family where you're using recursion, but not only do you care if there's a solution, but you want to find the optimal solution. So you would use branch and bound for optimization problems. Interestingly, with backtracking, if you're just looking for a solution, once you find it, you can stop. Branch and bound, you can't necessarily do that. You got to go through all possible permutations. And then finally, we have dynamic programming, everyone's favorite. And you use dynamic programming when you see that there's overlapping subproblems that you can store to reduce the time complexity and not recompute those. So here's a nice table that covers all the algorithm families and a little summary of each. Any quick questions on these? Today, we'll talk about branch and bound and dynamic programming. Actually, we'll also go over a greedy algorithm with Dijkstra's. Cool. Okay, so let's talk about Dijkstra's. Dijkstra's algorithm is very similar to Prim's. Nearly identical algorithms. And you use Dijkstra's when you want to find the shortest path between a given node and all other nodes. It's considered a greedy algorithm like prims, and it uses weights of the edges. The main difference from prims is you're finding the shortest path, and it can work on both directed and undirected graphs, where prims would need a undirected graph. Okay, so let's look at the algorithm. The setup, actually, let's talk about the setup first. Similar to prims, we're going to store a table of information that includes a Boolean for whether or not it's currently in the shortest path, distance for how close it is to a node in the shortest path. But here it would just be rather the distance from it to the current node you're looking for, the shortest distance for the node you're looking for. And then we're also going to store, to get to that shortest node, the shortest distance to the node, which node does this one go through? So the parent or the previous. So the setup itself looks pretty similar to prims. Really, the only difference is how we calculate distance. For prims, when we calculated distance in our table, it was the distance for your current node to any node in your MST. Whereas Dijkstra's is the distance from your current node to that specific node that you're trying to find the shortest distance. So the calculations are slightly different, and we'll see that with the example. We have a question. Does this answer the traveling salesperson problem? No, and that's a good question. So the traveling salesperson problem says you got all of these nodes. You have to travel to every single one of them without forming a cycle. What's the optimal path? Whereas this is just saying, if you're at a given node, what's the shortest path back to this specific other node? Do you see the difference there? So computationally, Dijkstra's is a lot simpler. Why does it say every other vertex? Let's see. Yeah, so it says the shortest path from a starting vertice to every other vertex. So for example, if we have our start be A, then it's going to give us the shortest path from B to A, the shortest path from E to A, the shortest path from F to A, the shortest path from C to A. So every other vertex, the shortest path from that vertex to the one we chose. Okay, so let's look at the algorithm. We loop V times. We find a node that we currently haven't visited with the shortest distance. We mark that to be true. It's currently now in our Dijkstra's algorithm. Then we look at every other one we haven't visited yet, and we say, update the distances, essentially, if we haven't done that yet. Very similar to prims. So let's go through an example. So depending on which node you want to be the shortest path to, in this case, let's say A. We want to find the shortest path from every node to A. What we're going to do is we're going to start with A being 0. So instead of infinity for the distance column, we're going to set it to 0. Okay, so now with our algorithm, we iterate through the column and we find the shortest distance that is currently not true. And that's going to be A. So parent of A, nothing, and we set that to true. So now A is in our algorithm family, our Dijkstra's or whatever. Okay, and now that we set A in here, we update the distances to everything that it's adjacent to. So A is adjacent to B, and it has a distance of 6. And when we're calculating distance, we say, okay, is A's distance plus the edge of A to B, which is 0 plus 6, less than B's current distance? So is 6 less than infinity? Yes. So we update that to 6, and then we say its parent is A. And then we would do the similar thing for C. Is A's distance, which is 0, plus 4, less than infinity? Yes. So we update that. We say that's from A. Okay. So we're done with that because A is only adjacent to 2 nodes. And now we find the next one with the shortest distance column that's not currently in, and that is C. So we set C to be true, and we throw that in. Okay, now that we did that, we have to update distances for nodes that are currently not in. C is touching B, D, and F. Okay, so going back to prims, when we're figuring out the distance from C to B, in prims, we'd say, it's 1 is the distance, right? We're seeing if 1's less than B's current distance. But here, we're going to say, okay, C's current distance plus this weight less than B's current distance. And in other words, the way that you can think about that is, I'm trying to find the shortest path from B to A. We currently have something here. We say the shortest path from B to A goes through A, this edge right here. And we're saying, if we instead went to C and then took C's path to A, would that be better? If so, update it. And that's essentially what we're doing here. So we say C's current distance is 4. 4 plus 1, is that better than B's best so far? It is. So that gives us 5. And we say, okay, to get to A, you're better off going through C. And then we go to D and we say C plus 5 gives us 9. Is that better than D's current, which is infinity? Yes. Goes through C. And then F would be 11. Goes through C. Okay, and that is all the updating that we can do. So now we make our next iteration. We go through the distance column, find the shortest one that's currently not in, that gives us B. So we set B to be in, and then we update distances of all the ones that are currently not in. Okay, so D, B's distance is 5. So 5 plus 2, is that better than D's best so far? 5 plus 2 is 7. 7 is better than 9. So yes, D, you're better off going through B than you are going through C. And that's kind of interesting because B does go through C, but it takes a different path to C. Okay, and then also we got E. B's distance is 5. 5 plus 2. Is that better than infinity? Yes. Go through B. And then that's the only ones that B is adjacent to that are currently not in our shortest distance. Okay, and then that's it for B. Go through our distance column. We got D and E and F. Both of those are 7, D and E. Let's just take the first one. Let's break the tie that way. You should be able to take either one unless on the exam it specifically says break ties this way. It might say on the exam, if there's a tie, break it by taking the smallest vertex or something like that. But we're not told how to break ties here, so we're just going to take D. So we're going to add D, and it doesn't really matter because D is not touching anything that's not in yet, so we don't update any weights, and we're done with that. Okay, now we're going to go to the next shortest one that gives us E. We add that. And we look at our only one that's adjacent that's not in yet, and that's F. And we say, okay, the distance from E to F is 3. 3 plus 7, because that's the current distance of E, gives us 10. Is 10 less than 11? It is. So that gives us 10. And instead of going through C, we go through E. Then last one is F, not touching anything that's not currently in, and we're done. So here's our table now. We calculated distances a slightly different way. And what does this tell us? Well, now we have the shortest distance from any node to A. So if we look at node B, we know the shortest distance has a weight of 5. Node E, the shortest distance, has a weight of 7. And I guess the question now is, what if we want to find the path? That's a good question for you guys. if I want to find the path from, say, vertex F to A, how do I do that? Our distance column tells us what the weight is of the shortest path, but how do we actually find the shortest path? Using the information that we calculated here. Yeah, you just follow the P column until you get back. It's almost like a form of backtracking. So if we want to find it from F, we don't know from F to A yet, but we can look at F's parent column and we see that it's E. Whoa, what did I do there? We see that its parent column is E, so it must have taken that line. And then we look at E's parent column and it's B, so it must have taken that line. And we look at B's parent column and it's C, so it must have taken that line. And we look at C's and it's A. So we can backtrack from the parent column to figure out the path itself. We had a question, do we go through the vertices linearly to find which one is the shortest that isn't T? Yes, exactly. So this algorithm is going to be n squared, where n is the number of vertices, because you have to go through all the vertices, which is n. And then for each vertex, when you add it, you have to do a linear search through all the ones and check, is this not in it? Is this adjacent? If so, update its distance. And then you also have to do a sequential linear search to figure out the next shortest distance, just like prims. So you can imagine you'd implement this with, a nested for loop. Okay, any questions on this? Any other questions? In what scenario would you use this versus prims? Okay. Yeah, that's a good question. What's the difference? So Dijkstra is what we're doing here. Remember, we calculate the distance columns differently than we do in prims. The algorithms are very similar, but they're not the same. The way that we walk through the algorithm is similar, the setup of the algorithm is similar, but really the key difference is when we're calculating distance. In prims, we say, what's the shortest distance from this node to any node in our MST? And for Dijkstra's, we have to consider this distance column as well. So the question is, when would you use this over prims? Prims figures out an MST. So at the result of prims, you have the minimum spanning tree. Dijkstra's gives you the shortest path from any node to your starting node that you decided. So they're actually quite different things that they're solving computationally. Cool. And that is what we did. Okay. Let's talk about generating permutations. I think this is like what Android passwords used to have that, if I recall correctly. And in this example, it looks like you can visit every vertex up to 1 time. So if you forgot your password, you would have to try all like n factorial combinations. Okay. So we can think of permutations as being part of a tree. For example, if we wanted to figure out all the permutations of 4 colors, in this example, blue, yellow, red, green, we could imagine those as being in a tree, where let's say that we first considered the color blue, then we considered the color yellow, then red, then green. That would be one permutation. A different permutation would be blue, yellow, green, red. So you can imagine that at the base of this tree, it could almost be like all the permutations, where I want to find a better color, where this permutation would be on the very end would be green, red, yellow, blue. This permutation right here would be red, yellow, blue, green, and so on. If we wanted to use a tree to enumerate all these permutations, there's two ways to do that. We could do a DFS or a BFS, right? Because those are two ways to traverse a tree. And once we made it to our leaves, that would be a given permutation. So let's talk about, time complexity wise, using a breadth first search versus a depth first search would be the same, right? Because we have to go through every one of these little nodes in the tree. But let's talk about space. What would be the space complexity of doing a depth first search here? In terms of n, where n is the number of colors. In this case, n equals 4, because there's 4 colors. So using a DFS, what would be the maximum space complexity for this tree? O of n. That's one of the answers that we got. And I agree with that. Because if you traverse this tree using a depth first search, what would that look like? Well, you would likely go down blue first, then yellow, then red, then green. So you go down this path. And then you get an answer. And then you'd go up, you'd remove that green, you'd remove that red, and you change it out with a green, red. You'd go like this, right? And then you go up here and go like this. But you notice that your stack frames never exceed n. What would our space complexity be if we did a breadth first search? Yeah, exactly. It'd be the height of the tree for the depth first search. And the height of the tree here is O of n. So that was the DFS. What would the BFS be? Well, the BFS, the traversal, would be like a level order traversal, right? So we'd kind of traverse it like this. And then finally, we get all of our answers in the last one. And the answer to this student answer is n factorial. Exactly. So at the base of our tree, we have all possible permutations, right? If n is 4, all possible permutations is 24, which is the same thing as 4 factorial. Because it'd be 4 times 3 times 2 times 1. So as you can imagine, in this example, it would be much more beneficial memory-wise to use a depth first search over a breadth first search. Where's our answers? Right there. Any questions on these memory complexities? And now you can also begin to see when we're doing permutations, permutation algorithms, why we use recursion in depth first searches. Your computer might explode if you try to use like a breadth first search. All right, looks like there's no questions. Let's continue. Okay, so the actual code for generating permutations. So this looks like a pretty straightforward backtracking algorithm. Right here is if you have a solution. And then right here is you recurse. These are pretty difficult to wrap your head around because it's using recursion and it's not that straightforward. So it looks like we have two things in our function. We have a vector of items In this case, we can imagine our vector of colors. And then we have an integer that says n fixed right here. You can imagine that n fixed is saying like, okay, all the indices right here and to the left are fixed. Those are not going to be swapped down this current path. And then what you do is you just run a for loop and you say, okay, a for loop from n fixed to the size of my vector, because I'm going to keep everything to the left of n fixed. And everything to the right, I'm going to generate all possibilities. I'm going to make a swap, and then I'm going to fix that swap and recurse down further. When I get back, I'm going to undo that swap, and then I'm going to try another swap. So you can see this here, we're doing a for loop and we're trying one swap beyond n fixed because I starts at n fixed and it iterates further. After we make that edit, we make that swap, we recurse. And when we recurse, we are essentially fixing that swap that we made for the future recursion. Then when we get back into the stack frame, we can imagine that all that future recursion down the line has already been sorted out. We can swap back to our original. Pretty difficult conceptually. I highly recommend that you try to convince yourself of this. And one way you could do that is you could walk through this tree right here. I would walk through this tree and I would have my vector of items fixed be, blue, yellow, red, green. So like blue, yellow, red, green. Initially, fixed is going to be 0. And this would be the first call of gen perms. And if you walk through this, you can see that you're going to generate all possible permutations of this vector. I think that this will be beneficial for the exam, but also for project 4 if you haven't got to part C yet. This is essentially the format of part C because this is like the basic format of branch and bound algorithms, where you have this fixed indice. You start at that fixed indice and you go beyond, you recurse down the line after you make a swap, you revert your swap and keep on adjusting fixed. I think it'll take some time to think about, but does anyone have any questions right now? It's kind of similar to in lecture. They might have gone over the beginning of the semester, a juggling problem where you use like a stack, like a vector and a queue or something, and you juggle between them to calculate the permutations. It's kind of similar to that. All right. Are there any visualizations of this that you know of? That's a really good point. I think that would help a lot. Not off the top of my head, no. But I wonder, I'll try to find something at the end of lab, because I wonder if you could just like look up like generating permutation visualizer. I'm sure it's a pretty common thing. But also like if you have something that's like a small sample, something like this, or you could even do like 3 letters. You could always just try like starting with this, a vector of just blue, yellow, red. The number of permutations for that should be 3 factorial, which would be 6. So you could like walk through an example by hand. And I think that would help a lot. Okay, sweet. So assuming this code, let's imagine that for the is solution portion, you did something like print out your vector, then that will find all permutations of 1, 2, 3 if your vector is 1, 2, 3, and it would list them out like this, or 1, 2, 3, 4 rather. All right, so gen perms is a procedure that it'll generate all the permutations. So if our vector size was 7, A, B, C, D, E, F, G, the number of permutations would be 7 factorial, and that would generate 720 permutations. Which of them would start with ace? Well, that would be 7 factorial minus 3 factorial, or it'd be 4 factorial rather, because then you'd only consider the last points, the last 4 letters. So you could say that 4 factorial start with ace, 24. Any questions on that? Because essentially you're cutting off the first 3 elements. Okay. Oh, and this is a good example too. So we talked about ace. Which of these permutations would start with ace? We said 24. So if we call gen perms with our vector A, B, C, D, E, F, G, D, or sorry, A, C, E, B, F, G, D, and then a fixed of 3, that would generate all permutations that start with ace. Because remember that our fix says that everything before this indice is fixed, we're not going to modify it. And it would essentially cut the vector down to generating all the permutations of B, F, G, D appended to ace. Any questions on backtracking before we talk about branch and bound? Remember, backtracking, branch and bound are both recursive algorithms. Backtracking is for constraint satisfaction, finding a solution. Branch and bound is for optimality. Okay. So the basic of branch and bound. So the basic of backtracking, we said, is solution recurse? We first check to see if it's a solution. If so, we do something, do some work, and then return. Otherwise, we recurse. Branch and bound is pretty much the same, except we have one additional component, which is promising. And we typically put that before the is solution. The reason we have that one additional component is promising is because remember, with backtracking, once we have a solution, we return, we're happy. With branch and bound, we have to go through all possible solutions. So we have to, do an iteration through the entire tree. But since we're calculating optimality, we're trying to find the optimal solution. If we know going down our current recursive path that we're guaranteed it's not going to be optimal, then it's pointless to go down that path. So we can just prune it. So the is promising component of branch and bound is essentially pruning, which is characteristic to branch and bound problems. Question is, can we use branch and bound optimization, that is promising optimization, that pruning, with our gen perms code? What do you guys think? So that is promising component. That optimization is for optimality problems. If we tried using that on our code for gen perms, what would happen? For example, say that we pruned that branch. We would lose all the permutations in that branch. So it wouldn't really apply or be a good idea to use pruning in our code for generating all permutations. Okay, so we essentially said that branch and bound is similar to backtracking, but we have this optimization is promising that lets us prune. So how do we do that? How do we prune? With these optimization problems, we can determine how to prune by using bounds. And we got two bounds. We have an upper bound and a lower bound. Our upper bound is our best solution we found so far. And our lower bound is an optimistic estimation for the remaining solutions going down the current branch we are. So when we're determining whether or not to prune, if we have this lower bound that is this, optimistic estimation, then if we do lower bound plus our current distance or our current weight, whatever the problem is, that'll tell us the best scenario that we could possibly get for going down that current branch. If we have this estimate that says going down this branch, it'll be no better than this. Then you have your current weight. If you add those two together, that's a best case scenario. It might not be your solution, but that's best case for what your solution could possibly be. So that being said, if that lower bound plus current estimate is less optimal than your best found so far, your upper bound that you've already calculated, then you would know that going down this branch is pointless, that it's impossible for it to be better than your upper bound. And it's impossible for you to find a better upper bound. So you can prune that branch and move on to another. That's kind of tricky. Let's walk through some visualizations of that. So let's say that we have a minimization problem. And you know what? Let's apply this to project 4. So for project 4, you're calculating TSP. You're trying to find the minimum cost for connecting all of the nodes without creating a cycle, or I guess one cycle. So you only want to visit all the nodes once and you want to find the minimum cost. So let's say that here is your current cost. And of the path you're going down. And right here is your upper bound, best so far. And what best so far is saying is you've already gone down some other path, and that is the best path you've gone down so far, is best so far. And so that's our upper bound. Okay. Anyway, right now we're recursing down our current path. We also have this optimistic. And our optimistic is saying, what is the optimistic? The optimistic is the lower bound plus cur. So remember, the lower bound is the remaining, in this case, the remaining nodes that are currently not in our path. If we connected them in the best possible way, how much would that cost? Okay, that's our lower bound. So our lower bound plus our current says this path that you're on right now, if the stars align, everything works perfectly, this is the best solution that you'll find. You're optimistic. Is that actually a solution? We don't know yet. We have to go down the path to see. But this path, the minimum weight you're going to get from this path, it would be impossible for it to be better than you're optimistic. And in this case, you wouldn't want to prune this path because your optimistic is better than your best so far. So, hey, you might be updating your best so far. So, kind of tricky. Any questions on this? Is it kind of making sense? I would say, like, for the most difficult concepts in this course, I would say that DP and branch and bound are definitely up there. They're quite difficult to get conceptually. So remember, upper bound is your best so far. Lower bound is your optimistic estimate for the remaining nodes currently not in your path. And then we got to juggle those two to determine whether or not we can prune our path that we're going down. So here are 3 examples. And I want you guys to tell me, here's our current path. We want to determine whether or not we can prune this path and go on to another one, or if we have to go through it, because we might be updating our best so far. So here's our current. The lower is the better on this scale. Here's our optimistic, which is our lower bound plus cur. Here's our upper bound. And then possible is our sample space for what the possible weights are. Remember, it would be impossible for the possible weights to be better than our lower bound plus the current, because that is our optimistic estimate. But they can always be worse. So can we prune this one? How do we determine the lower bound? Good question. So the lower bound is the remaining nodes, the best way to align them. That's a difficult thing to determine, right? But we can overestimate. We can, use some heuristics to maybe come up with a solution that might be better than what could possibly happen. So, for example, let's say that we have these nodes and we have to start right here. And here's our current path. Oh no, I gave away the answer. So let's see if I can make a visualization of this. So let's say that this is our current path and we're right here and we got to connect to these last 3. So we have to somehow think about a way to connect those last 3 to give us a lower bound, an optimistic way, best case scenario, how to connect them all. Any ideas? If you're given a certain amount of nodes, what's the best way to connect them? Say you're trying to minimize the weights of connecting them. An MST, exactly. So let's say, to visualize this example, let's say that current, we're at these 4 nodes, and those 4 nodes are connected in our current path. Now, whatever our TSP of this entire thing, it's going to be somewhere along this weight, this possible. But we don't know what our optimal is yet. But an optimistic estimate for all the nodes that are currently not in our path would be an MST between them. So if we calculated MST, then connected that MST to our current path, that would give us a lower bound. No solution that we come up with could be better than this. It's worth noting that this is not valid. That's not a valid TSP. But that's not what lower bound tells you. Lower bound tells you that your answer is no better than this. It doesn't necessarily have to be possible. So for the TSP problem, yeah, using an MST would be a pretty good idea for how to connect those remaining nodes to calculate your lower bound. So does that answer your question? Is this a possible heuristic for part B? Remember, part B is fast TSP. Part B is you're trying to calculate a quick heuristic for the traveling salesman. And it has to be an answer that is, I'm trying to think. So they're answering different things. An MST is not the TSP. But this is a valid way to calculate your lower bound for part C when you're calculating opt TSP. I think that there are some fast TSP heuristics that use MSTs, but you couldn't just calculate an MST for part B and print that answer. Because remember, part B has to be some answer that's not optimal, but it can't be better than optimal. It's got to be some answer that you calculate that's probably not optimal, but it would work, if that makes sense. It's a fast approximation of TSP. Okay, so anyway, going back to this, I think I already showed the answer, but does everyone understand why in this example you would not be able to prune because your optimistic thought is better than your best so far? So you could potentially be updating your best so far by going down this path. Make sense? It's possible that a better path exists. So now let's go on to the second one. So here Kerr is our current path. And here's our optimistic estimate, which is our lower bound plus our current path. Can we prune this path? Obviously, the remaining possible answers are going to have to be no better than our optimistic estimate. Can we prune this? Yes. So in this case, you could prune this because if you look at your best so far, your upper bound on the answer, it's better than your optimistic answer for going down this list. Since we have a minimization problem, the further down, the better. So in this case, you know that following through with that current path, your final answer is not going to be better than your best so far. So it's pointless to go down that path. Okay, and then we have this final one. So here's our current path going down it. We have our best so far, which we've calculated our best path going down so far. And then our estimate is right there. For if everything works perfectly, this is the best possible answer we get. So do we go down this path? Can we prune it or do we have to go down it? Yep, you got to go down it because optimistic is better than your best so far. But it says that it's doomed to fail. Oh, okay, I see. I think these slides are messed up. Okay, yeah. So it's saying it's doomed to fail because even going down it, you're not going to be better than optimal. Okay. So big picture with this, we have this upper bound and we have this lower bound and we have our current path. Upper bound is our best so far. The lower bound plus our current path is this optimistic estimate. We can use this to prune to decide whether or not we want to go down the path. And this is used for pruning and branch and bound problems. Any final questions on this? Okay, take some time to convince yourself that you understand that it's a pretty important concept for the project as well as for exams. So let's talk about over pruning and bounds tuning. So like we said, we have some invariance with this upper bound and lower bound. Our upper bound is the best solution we found so far. So of course, that has to be greater than or equal to the optimal. In other words, it has to be worse or equal to optimal solution, because we couldn't find a solution that's better than the optimal solution. An invariant for our lower bound, which is our optimistic estimate, has to be less than or equal to the optimal solution. So in other words, it has to be better or equal to optimal. The reason that our lower bound has to be better or equal to the optimal is because if our lower bound was worse than our optimal, if we said that, going down this path produced you a worse solution than optimal, you would never go down that path. Or rather, connecting, I guess the question here is, if we said that connecting all of the nodes going down that path produced you a solution that was worse than the best possible way to connect them, you would always prune. So here's our invariance for the upper and lower bound. And if this relationship is violated, the bounds are invalid. So running through an example, if our upper bound is invalid, which means that our best solution we found so far, invariant, is invalid, then we'll never find a solution. Whereas if our lower bound is invalid, and we say that, our lower bound is a worse approximation than the optimal, then we might accidentally prune that lower bound or prune that path when we shouldn't have. So an example of that, going back to this MST, remember how we used an MST to calculate that lower bound for the remaining ones. The reason we use an MST is because we're saying that connecting those last four could be no better than this. This is the best possible way we could ever connect something. That's our lower bound, right? If that invariant didn't hold and we said, actually, let's say the best possible way of connecting it is like this, then if we're here, of course, we'd be like, whoa, there's no way that we're going down that path, when it might actually produce the correct solution. So one of the invariants is that when we calculate that lower bound, it has to be better or equal to the best possible way to connect them. And that's what we're saying. If our lower bound is invalid, we might accidentally prune when we shouldn't have. Okay, so now that we have these approximations with upper and lower bounds, there's a trade-off, right? And the trade-off is between accuracy and performance. So if we have tighter bounds, more accurate lower and upper bounds, we might prune more, and that would be faster. But we also need to consider the cost of calculating those bounds. If it takes a long time to calculate those bounds, doing that calculation might be not worth just going down that path. So in other words, like if the cost of computing is more than the time saved to pruning, then the whole point of calculating those bounds is useless. So there's this trade-off between how tight you want the bounds and how much time it takes to calculate that bound. And there's not necessarily a correct solution. You just have to experiment to determine what are the fastest bounds. Okay, so here would be a branch and bound solution to generating and pruning permutations. So like we said, 3 steps. We have this recurse step. We have this is solution step. And in this case, is solution is above is promising. And then we have this is promising step. And that is the general layout for a branch and bound algorithm. And on project 4, your algorithm will look pretty similar here. You'll have to write the is promising function. You'll have to write the code inside the is solution. And that's pretty much part 4C. Didn't we say that we can't do branch and bound plus permutations though? So kind of a different example. We said that in this example, when we wanted to generate all permutations of those 4 letters, we couldn't use branch and bound because we would prune some branches and not generate all permutations. But when you don't care about generating all permutations and you just want to find the optimal ones, for example, if you're generating permutations of paths to follow to find the TSP, if you only care about the optimal paths, it's fine pruning and not looking at some of the permutations. Cool. Okay, that is generating permutations, branch and bound, and backtracking. Any final questions on this before we go on to DP? You'll need to have a pretty good idea of branch and bound for part C of project 4. Lab recordings are on YouTube. If you go to the Dijkstra YouTube channel. Does part B not use branch and bound? No, because branch and bound is used when you're trying to do an optimization problem. You're trying to find the optimal solution. Part B, we're doing a fast TSP. We're not finding the optimal TSP. We're going to use a heuristic instead. That gives you something that's pretty close. It's not perfect, but it's fast. Part C, we're saying you have to solve TSP. Solving TSP is n factorial. So if you don't do any branch and bound, if you don't do any pruning, it's going to take forever to solve that. Yep, no problem. Okay, cool. Dynamic programming. All right. So with dynamic programming, you're trying to answer every subproblem. And the key factor with dynamic programming is that the subproblems overlap. And once you identify that they overlap, you can save those subproblems, only calculate once. And typically what that does is it turns like a polynomial solution, or rather an exponential solution, down to polynomial. And dynamic programming typically trades time for memory. You save time, but you use more memory. Okay, so let's look at Fibonacci. When we're calculating f of 6, Fibonacci of 6, how many times do we end up calculating Fib2? You know, and we can look at this tree, we can see that we're constantly calculating Fib2. And because of that, you know, the naive Fibonacci solution is exponential. It's essentially a tree. But if you saved Fib1, Fib2, Fib3, Fib4, Fib5, you can use DP and bring this exponential solution down to O of n. Because we can identify that there's a bunch of overlapping subproblems. Only calculate those once, refer to our calculated values in a memo table instead of recalculating them. You know, the second, third, fourth, and in this case, the fifth time we call Fib2. So let's go through an example of that. With dynamic programming problems, you can solve them. Doesn't the recursive solution save the earlier ones though? Well, let's go through that. So here is our naive recursive solution. Yeah, so let's go through that. So we're calculating Fib6, right? And we look at our naive solution and we say, okay, to calculate Fib6, we have to calculate Fib5 and Fib4, right? So to get this solution, we have to call this one and this one. But I think you see like, yeah, it's saving it for a specific, going down a specific tree. But between these two, you know, 5 and 4, they're both going to calculate 2 multiple times, and it's not going to be saved between those calculations. So yeah, in this problem, you see that there's a bunch of overlapping subproblems. Let's throw those into a memo and only calculate them once. Okay, so with dynamic programming problems, we have 2 ways of doing the calculations. We can do a bottom-up approach or a top-down approach. Let's start with the bottom-up approach. And let's not look at the code yet. So let's imagine we have this memo table, little vector. And the index in the vector says the answer of that fib. So the index right here would say the answer to Fib0. The value at that index would be Fib0. The value at this index would be the answer of Fib1, the answer of Fib2, all the way up 3, 4, 5. And I guess the key idea behind this is saying, okay, you know, if I throw my answers into a memo table that looks like this, then when I'm doing my calculations for when I fill up this memo table, when I end up getting my answer to Fib5, you know, I can just return that answer. And let's say the answer is like Fibonacci of 5. We made this memo table. We can just return whatever is in that last box because we say that at that index, that's the answer of Fib5. So we have this memo table that tells us, you know, if you want that fib, just look at that index in the vector. Does that representation make sense to everyone? Because the next key point is how are we going to populate this table? What if this uses a ton of storage? Let's not think about recursion at all. I mean, right now, for fib of 5, my vector is only 5 elements long, right? So that would just, that's not that much storage. let's say that we had like fib of 30. We would have to create a vector that's like 30 elements long. 31, I guess. So if we could have this vector representation where the index refers to that fib, the value at the index refers to the answer at that fib, then, if we wanted fib of 5, we would just declare a vector of size 5 plus 1, and then fib of 5 would be the value at the very end, right? But you don't use some of the spots in between, right? Yeah, but this is going to be like, let's say that n is the fib that we want to calculate. It would be O of n for space. So now that we have this representation of like turning this into a table, how do we populate this table? Well, there's a few base cases. What's the fib of 0? Zero. What's the fib of 1? That's easy to fill out. Fib of 1 is also 1. Now, how do we fill out the rest of this vector? Trying to find fib of 5. Fib of 5 is going to be at index 5. And I guess, what is fib of 5? That's fib of 4 plus fib of 3, right? So if we wanted to find the answer here, we would have to look at the answer at these two. But we don't have those. So if we wanted the answer here, we'd have to look at the answer for these two. Don't have those either. What we can iterate through this left to right, and we can say, let's just solve the remaining number of these blocks. What's the answer of fib of 2? Well, we can look at the answer of fib of 1 and fib of 0 and add those two together to get 1. And then, we can iterate to the next one, and we can say, okay, this one's going to be 1 plus 1, which is 2. The next one's going to be 2 plus 1, which is 3. The final one's going to be 5. And then we could just return that. Does that make sense? So the bottom-up approach is we create this memo table. And that memo table is the Fibonacci answer at that index. And the size of this memo table is going to have to be whatever fib we want to calculate plus 1. Then we fill in our base cases in this table for fib of 0 and fib of 1. And then we just keep on iterating through it, calculating each box until we get to our last one and return the value at that last one. And what this is essentially doing is we're only calculating fib of 1, fib of 2, fib of 3, all of those one time, rather than with the tree recursion, calculating them multiple times. And you would see, if you wanted to see the code, it would look something like this. We're trying to find fib of n. So we create a vector of n plus 1 because it's 0 indexed. We fill in our base cases. Then we iterate to this vector up to n, filling in the fib of that index. And then we just return the last index in our vector. This is going to be O of n runtime and O of n memory. And really conceptually, the key part of this problem is this memo table right here. Any questions on this? So this would be the bottom-up iterative approach to the DP Fibonacci. Okay. So we could do top down as well. We can use recursion, and rather than creating a vector, we could, well, rather than iterating, we could recurse. So when we're trying to calculate a fib, we just check to see if we already have calculated that value. If so, we return it. Otherwise, we calculate it. So here would be like implementation of that. Here, our vector is our memo table. It's a global vector. And we make a call to fib of n. And I say that, okay, if our memo table is empty, which means that this is probably the first call we made, let's resize this memo table to be n plus 1. Whoops. So in this case, if we're doing fib of 5, we're going to resize this table to be length of 6. 1, 2, 3, 4, 5, 6. Okay. And then the next condition is n less than 2, return n. It's not, it's currently like 5. And then we say, have we calculated out the memo for 5? We have not. So then it says calculate that memo and then return it. So then it tries calculating that memo. So it jumps to these two spots. And it says, okay, have we calculated these? If not, try to calculate the memo previously. And it jumps down, jumps down, jumps down. Eventually it gets down to the base case. And it'll return 0 and 1 for these base cases right here. And then it gets back into those previous stack frames we called. And it, for the ones that haven't been called yet, it'll say, have we calculated these yet? And it says, yes. Okay, return it. And then it'll slowly build it up top down using recursion. And since we have this check right here saying, if it's not been calculated yet, calculate it, we're only going to calculate it once. So it's also going to be O of n, memory, and O of n, space. On an exam, when you're doing the DP problem, you're welcome to use it bottom up or top down, whatever is easier for you to visualize. Questions on this implementation? This might be kind of tricky. This is the same thing as saying if memo n equals 0. Won't it be, yeah, it'll be filled in with default values, so they'll all be 0 initially. Okay, so that's the top down and bottom up versions of fib. I want to do another problem too. And this is like a fun problem that I like. But before we go on to that problem, I want to make sure that everyone has a start to like understanding how the memo table works, especially for the bottom up approach. Can you explain the difference between the top down and bottom up a little bit? Yeah. So the generally in top down, bottom up, top down starts with your answer and it keeps on calling smaller ones until it works its way back up and you return your answer. Whereas bottom up is you create the memo table on the spot and you start calculating the smaller ones until you work your way up to the top. So in this case, with top down, we tried to start at the top and we said, hey, can we calculate this? Have we already calculated it? No. All right, calculate the next ones. Have we already calculated these? No. And then we make it down here and we start calculating them and work our way back up. Whereas bottom up says, I want to calculate this. I'm going to declare a vector. I'm going to iterate bottom up on the vector until I get this answer. So that's conceptually how they're different. In practice, how they're different is top down uses recursion, bottom up uses iteration. Cool. Okay, so let's go on to minimum path sum, a fun DP problem. So we're given this M by N matrix, and we want to find the minimum sum path from the top left quadrant to the bottom right. And then we have this note that says you can only move down or right at any given moment. Okay, so it's saying that we have to start here and we have to end here. And we have to figure out the minimum path to get from the start to the end by only moving right or down. And in this example, our output is 7. And as you can see, our output is 7 because we can take this path. So it'd be, 1 plus 3 plus 1 plus 1 plus 1, giving us 7. We could try to take a bunch of other paths. We could try taking this path, but doing so, it would be 2 plus 4 plus 2 plus 1, which would be 8. And no other path would be better. So how do we solve this? And to solve this, I kind of want you to think about the fib problem that we just did, especially the bottom up. So if we had a separate vector of the same size, so you're saying a separate 2D vector, and then we put the sums of the adjacent value in the vector. And then when you go diagonally, find the minimum sum. Okay, I think you're onto the right point. Okay, yeah. So the way that I would think about this is I'm starting here and I'm ending here, right? So if I was right here, what are the possible ways I can get here? Yeah, I think you're onto the right track. But I also want to ask you how you fill your memo table. But anyway, before we even think about a memo table, and we're trying to calculate the answer to this problem, when we're at this point, the final box we have to be at, what are the possible ways that we can get here?
Any permutation of 2 right and 2 down.
2 right and 2 down. So like you're saying like here, what do you mean?
Yeah, so like there's different paths, right?
Yeah.
So like right down, or just like any permutation of those.
Well, really, there's only 2 places that we could have came from. We could have came from this box or this one, right?
Yeah.
So I guess my thought is, let's say that we had the 2 answers for this box. Let's say that we had the minimum sum of getting here, and let's say that we had the minimum sum of getting here. How do we solve our answer? Take the min of those 2 and add 1 to it. Does everyone see that recurrence relation? So we know that our answer has to be the minimum sum of this box. To get that answer, if we know that we had to come above or from the left. So if we had the minimum sum of this box and the minimum sum of this box, then we could just see which one's less and then say, okay, that's where I came from, and then add 1 to it. And that will give us our output. So if we had the minimum sum of those two boxes, we could find our answer pretty easily. Okay, well, I mean, how do we find the minimum sum of these two boxes? Well, when we're at 2, how do we find the minimum sum of 2? You'd have to have the minimum sum of these two boxes, and then you add 2 to it. Or take the minimum of the minimum sum of those two boxes and add 2 to it. And that process continues. And as you can imagine, when you're calculating the minimum sum of this box, you're looking at the minimum sum of this box and this box, taking the minimum of those two, and you can see that there's a bunch of overlapping subproblems. So let's make a memo table. And for this memo table, as Nithya mentioned, we're going to make it a 2D matrix. And right now it's empty. And the representation of this memo table is at this box, any given box, the value at that box is going to be the minimum sum of it, ending there. So the value at this box is going to be the minimum sum to end at that box. So what's our final answer going to be? It's going to be returning this right here, because that's the minimum sum of ending at that box. Everyone agree with that? So we have a memo table, and each box says the minimum sum ending at that box. And once we calculate the value at this box, we just return that and we have our answer. Okay, so now the question is, how do we populate this box? 2 approaches. You can do top down, you can do bottom up. Top down would say, okay, see if there's an answer here. If not, find these 2 answers, take them in, add whatever this is. And then you'd say, okay, for these 2 answers, see if there's an answer here and here. If not, find them. And eventually you'd have to have a base case, so it populates it. But we could also do bottom up too. And I think we're going to do bottom up because I think it's easier to visualize. So anyone have an idea of how we can start filling out this box? What's a good place to start? We just identified our recurrence relation. And our recurrence relation is, for a given box, the answer to that minimum sum of that box is going to be the minimum sum of the left box and the box above, the minimum of those 2, and then adding to it the value at the current box, which we can get from our previous table. That's our recurrence relation. But how do we start filling out this memo table with our base cases? Start with the top left. Yeah. What is the memo? What is the minimum sum to end at this box? It's going to be 1, right? Because the minimum sum of ending at that box is just going to be the value at that box, because that's where we start. That's easy enough. Any other suggestions for where it might be easy to start filling out too? What about this one? What are the possible ways that we could have got to this box? Right. So we could actually fill out the entire top row and left column, because the only way that we could have got to this box, remember up here, the only way that we could have got to this box was from the left, because there's no boxes above it. So we can say that the minimum sum of ending at this box right here is the box to the left plus the value at this box. So the minimum sum of the box to the left is 1, plus the value at this box is 3. So the minimum sum to end here would be 3 plus 1, which is 4. The minimum sum to end at this box would be, the only way to get to it is to the left. The minimum sum of the left is 4, and we have to add 1 to it from this to end there. Okay, so that's the top row. Then we can do the leftmost column as well, because similar logic to above, the only way to get here is from above. So we can say that the value here is the minimum sum of above plus the value of this box, which is 1. So 1 plus 1 is 2. And then this would give us 2 plus 4, which is 6. And right now in our table, we just filled out the minimum sum to get to the top row and the leftmost column. Everyone agree with that so far? Any questions on that? So what I would do if I was doing this bottom up, I would say, okay, I'm going to iterate through the topmost row. Now I'm going to iterate through the leftmost column. And for the remaining parts of the table, I'm going to start at, I equals 1, j equals 1. So you start right here for the remaining, and then you fill in all this. So it'd be like a for loop, another for loop, then a nested for loop where I starts at 1, j starts at 1. Something like that. Okay, so now that we have this essential information, we can start filling in the rest. It's worth noting, however, that we have to start here now if we're doing bottom up. Because if we started here, we don't have the information left to it. So let's fill in this box. What's the minimum sum of this box going to be? Five plus 2, exactly. Because the only two ways to get to this box are from the left or above. So we're going to take the minimum of those two minimum sums, which gives us 2. And then we're going to add to it the value of ending here, which is 5, gives us 7. And then we can use the same logic here to get 6. Then we can use the same logic here to get 9. And now we're at our last box. And we say the only two ways to get here are above or to the left. We have those two minimum sums. We can take the minimum of them, which is 6. We can add 1 to it, and we get 7. And then we can return that answer. What's the time and space complexity of this? O of mn, time and space. Why can't we just do from row 0 and from row call 0 to calls? So what you could do, you could do that. You could do one nested for loop. You're just going to have a bunch of if-else statements. You have to have a if statement for if you're the top row. You have to have an if statement for if you're the first column. And then you have an else statement saying, okay, if I'm not the first column or the top row, then I can look at the other two. Is the bottom middle value 8? Oh, you're right. That should be 8 because 6 is less than 7. 7, so it'd be 6 plus 2. Okay, so that is a DP problem, minimum path sum, that uses a 2D matrix. Any questions on that? So I think when solving these problems, first you have to identify, like, you understand the problem. And then I think like the next aha moment was like, okay, I can only move down or right. And then figuring out like, okay, well, my last answer, the only ways that I could have gotten there was if I went from above or if I went from the left. So if I just had the minimum sums of those two, I could figure out the minimum sum of my current. And then from that saying, okay, so then I'm going to make a memo table that represents the minimum sums. And I'm going to populate that with the base cases, then the first row, then the first column, and then the rest. So with DP problems, there's only so many questions we can ask you. You have like a DP problem that's like count the number of ways. The min-max path, this would be like one of the min-max paths. Merging, decision, string, list, some examples of that. On Gradescope this week, you're going to solve knapsack, so that'll be a decision 1. We just solved one for the minimum max. In lecture, you guys did night moves. Maybe you could practice some of these if you wanted to on LeetCode. In the lab slides, we also have an example of pipe welding, which involves a merging combination DP problem, pretty difficult. And if you wanted like a walkthrough from that, you can go to the YouTube channel, East281 YouTube from fall 2020. And in lab, we discussed pipe welding. But yeah, if you're wondering like, how do I get better at DP? It just takes practice. The hardest part about DP is identifying that recurrence relation. And to do that, you just got to practice. That being said, you know, some advice if you're on the exam and you're doing that DP problem, because there's always a DP problem on the exam, and you're stuck, you don't know what to do, you know, fight for partial credit. Think about the base cases. Think about the memo. You can look at the time and the memory complexity to get an idea of what the memo might look like. And that's about it. For the handwritten problem, we have knapsack. And knapsack is that you have a weight capacity and you have n items. Each of those items has a value and a weight. And you want to try to maximize the value in your knapsack given a constrained weight limit. And that's it. Thank you guys. Last lab of the semester. Congrats again for making it through, and I wish you all the best of luck.